Hello, here is a follow-up video to our Costco Yardistry greenhouse. The greenhouse has been working well. We just stained it a few days ago and it's looking pretty good. Everything's holding up just fine. And it provided a season extension for us. We were able to get an early start in the spring. However, we were unable to use it during the winter because of just too much of a wild temperature swings. In the middle of winter, we might get up to, say, 70 degrees in the day, but would drop to ambient temperatures, so well below freezing, at night. There's just no thermal mass inside. Now, I could just run an electrical heater because I did plumb electricity to the shed, or the greenhouse, I should say, but I'm going to try to be green. What I want to do is use a drum in here, which I've filled full of water. This is 15 gallons of water, and I purchased two used 325 or 350 watt solar panels, and I'm going to use those solar panels during the day to heat up this barrel of water. And my idea is to have that barrel heat the greenhouse in the winter. We'll see how it works. I 3D printed some brackets to hold the panels onto the fence here. They're just a little come down and have a little J lip on them. My first trial didn't work so well. The panels actually fell off because these just weren't strong enough, or they basically deformed from all the heat. I may have to do this in metal, maybe a little aluminum bracket, but we'll give this a shot and see what happens. Here's an example of the temperature extremes inside the greenhouse. The Inkbird keeps a nice history of the temperatures that it's monitoring. And this is a temperature graph I've got from a local weather source. You can see that this was from several months ago. This is actually October, the tail end of October of last year. On this specific day, the Inkbird measured a temperature within the greenhouse of 72 degrees, and this weather service states that that day got up to 57 degrees. So we can see that the greenhouse is working, and it is warmer than the outside temperature. We can see here that that evening it dropped down to roughly, let's say, 27 degrees. So well below freezing. And the weather service states here 29 degrees. So 72 degrees down to 27 degrees. That's a pretty big swing in temperature. And this is what I would like to try to solve. Here's the plan. And why am I doing this? As I mentioned earlier, the greenhouse experiences very extreme temperature swings during the fall and the winter. It gets nice and warm in the afternoon, but will drop down to ambient outside temperatures. So just not usable without heating. I started looking at adding just a conventional electric heater, 1,000-watt heater, and it would probably be running all night long. So I'm an engineer, I'm a maker, I'm kind of a nerd, and I said, let's try to do this maybe a different way. And I know that water can store a lot of heat. So this is the idea. I have my solar panels here, and I'm using 325 watt panels. I have two panels. The nominal voltage I'm assuming is going to be around 30 volts. I have a DC to DC converter that I purchased from AliExpress for about 20 bucks. It's 600 watts, 20 amp rating with a maximum of 50 volt input. I'm going to use this DC to DC converter to regulate my voltage to 12 volts, and I'm going to set the current, the constant current setting to about 20 amps, maybe a little less. The output of this converter is going to go into a DC rated solid state relay. And then that goes into a heater, a 12 volt rated heater that's going to be inside this water barrel. I'll also have a temperature sensor that goes back to this Inkbird temperature controller, which I have talked about a little bit in earlier videos. The Inkbird is just going to be powered by my normal 120 volts AC. The output of the Inkbird, I will use the heating output, and it will connect to a little 5 volt USB adapter, which will turn the solid state relay on or off. So the idea here is that I'm going to set the Inkbird to 110 degrees Fahrenheit. And if the water temperature is below 110 degrees, it will apply power to this little adapter, which will turn on the solid state relay and will turn the heater on and heat up this water. Here is a nice graph that I found on the engineeringtoolbox.com. And this graph shows how much energy is stored in water. And I have a 15-gallon drum, which is approximately 60 liters. And I want to heat this water up to 110 degrees Fahrenheit from 40 degrees Fahrenheit. That roughly is a difference of 40 C. Now, I'll take this 40 C line, which is green, and then I'll take my volume, which is 60 liters, and then I'll look at this horizontal line, and that basically is stating that there's roughly 3 kilowatt hours of energy stored in this difference of 110 Fahrenheit to 40 Fahrenheit. Now, during the winter at our location, I might be getting around 4, maybe 3 solar hours. So if I estimate on the high side and take that 3 kilowatts, divide it by 4, that means that I would need 750 approximate watts of panels to heat up that water. And also, if I were to assume that a 18650 battery was 10 watt hours, I could take that 3 kilowatts, divide that by 10, and that would mean that I would need 300 batteries, 300 18650 batteries, to have the same amount of energy storage as 15 gallons of water. So this is all just some rough math, but I think it's pretty accurate. Here is the actual setup. I know it's kind of a mess. I'll walk you through what's going on. This is a AC to DC power supply. It's rated for 12 volts, 300 watts. This is simulating the solar panels. It has a trim voltage or a trim adjustment, and I trimmed it up to 14 volts. That's the maximum voltage it can go to. I probably need to go up a few more volts because the DC to DC regulator needs at least 3 or 4 volts above the voltage that it's trying to regulate. That's why I have it set for 11.2 volts right now. So I take the output of the AC to DC power supply, the solar panels. It comes into the input of the DC to DC regulator. I have it set for 11 volts, and I have the constant current setting set for about 20 amps. The output of the DC to DC goes to this solid state relay, and the output of the solid state relay goes to my Regal DL 3021, which is a electronic DC load. This is simulating the actual heater that I'm going to have inside the water barrel. Reason why I'm using this is I can easily turn up or down the amount of simulated heater power. Okay, so as we can note, right, oh, and then I have the Inkbird a controller, and we can see that my set value is set for 110 degrees Fahrenheit, and the current ambient reading it's seen is roughly 70 degrees. That is the temperature of the little sensor here. Since the present value, I'm guessing that's what the PV means, is 70 degrees, it's less than 110, that means that the heater should be turned on. So I'm using the heat output of their little dongle here. This is a USB adapter. The USB adapter is powering the control side of this solid state relay, and I'm saying heating here, and then I'm which is energizing the USB adapter, which is powering the solid state relay. And since that's turned on, we can see that we're getting the 11 volts to the actual heater. However, I don't have the load turned on, so I'm going to go ahead and increase that up to, let's call it 10 amps. I'm still getting about 9.5 volts here. We'll call it 10 for easy math, and we're about 95 watts. We can call that about 100 watts. Here's our 10 amps that the DC to DC is seeing. And since we don't have a feedback loop, we're not actually heating any water. This will be heating forever. What I'll do is I'll simulate the feedback loop by taking the thermal sensor here and putting it near my soldering iron, which is turned on. So I'll set that here for just a second, and we'll rapidly heat up this sensor as if it were in the water barrel and getting warmed by the increasing temperature of the water. Temperature is rising in the water, 103 degrees. There we go. So the heating turned off the adapter over here, and now the solid state relay is off, and we can see that we no longer have any power or voltage present on the heater. Once this is dropped down past 110 degrees, we'll turn the heater back on. So that is the basic system. I'm going to throw all of this into a box, and we will put it out in the greenhouse and see if we heat up the water. I'm in the dead of summer right now, so I'm not going to be able to do a whole lot of real testing because the water is going to be I wouldn't be surprised if the water is at 80 degrees just from heating in the greenhouse. And we can see that the heating turned back on, and we are pulling the 10 amps. I can move this up to 20 amps. You can see that the converter is supplying the 20 amps. If I go a little higher, we can see that the constant current mode has kicked in, and it has dropped it's still supplying 20 amps, but it's only dropped down to about 2 volts. Now, this is how I'm hoping that it can extract some good efficiency out of the solar panel. I would like to make custom hardware that actually does some maximum power point tracking, but that's a little down the road. We can see here, you're not going to be able to see it too well, but we can see that there's a red LED turned on right here, which is stating that we are currently in constant current mode. Here is the system that I'm going to put into the greenhouse, and I have this all hooked up to simulate and make sure that it works before I get out to the greenhouse. I have right here a 350 watt 12 volt AC to DC power supply. I have it trimmed up to its maximum voltage, which is about 13.5 volts. Over here I have my 300 watt 12 volt heater, submersible heater, and I have it in a bucket of water to dissipate the heat so I don't burn up the heater. As you can see, this is the system. I showed this in a block diagram. I'll just go over it here really quick. I've got the Inkbird controller, and it has a cooling and a heating AC output. What I have here in the heating output is a USB power supply, and this power supply will engage this solid state relay as well as turning on a circulation fan. The solid state relay is mounted onto a heat sink, and over on this side I have entry holes, and you can see the shadows there, and that will pull air across the heat sink of the solid state relay out of the enclosure. Here is the DC to DC converter, and right now I have the power supply turned on, and I have it set to regulate at approximately 12 volts, and you can see that there is no current being pulled from the heater. And the reason why is the Inkbird is turned off, which has the solid state relay turned off. So what I'll do is I will turn on the Inkbird system. This is my set point of 110 Fahrenheit, and this is the temperature of the water bucket. The idea is when this reaches 110 degrees, it turns off the heating, which turns off this USB power supply, which will turn off the solid state relay, and that will regulate the temperature in the water barrel. This unit is good for 20 amps continuous operation, so states their website. My first few tests with the solid state relay did not go well. It was getting really hot. It was too hot to touch the heat sink. I could smell it getting hot, and I was worried that this wouldn't hold up. I was doing my tests at 15 amps at that time, and what I did is I measured the voltage across the solid state relay. Here we're seeing 130 millivolts. The original solid state relay I had in there measured 1.1 volts, and so 1.1 volts at the 15 amps would be 16.5 watts. So that'd be 16.5 watts lost here rather than going over into the bucket. So I went and grabbed a bunch of different solid state relays that I have and measured their voltage drop across, and this one has the 130 millivolts, and the other units I had were all slightly over a volt. And so this has about 10 times less resistance, and the heatsink is ice cold. So kind of note to self, make sure you're always kind of checking that on resistance or voltage drop across your solid state relay. To show how this is going to work, I'll grab the thermocouple out of the water, and I'm just going to hold this thermocouple up to my soldering iron so I can simulate getting up to the set point of 110 degrees. So we'll warm this up. You can see the present value, the PV value on that Inkbird rapidly increasing. And as soon as it gets up to the 110 degrees, we can see that the solid state relay turned off, my ventilation fan turned off, and we can see that the red meter here is saying 12.1 volts. Blue LED up here, we're in constant voltage mode, and you can see here that very little current is being pulled through the system. This is probably just an air voltage. It should be basically 0. If we watch this for a second, it's going to pass that 110 Fahrenheit, and it will re-engage the solid state relay, the fan, and we'll start current limiting here again. There it goes. In just a second. There we go. Well, that is the plan, and we will see how it goes. I will do a brief video with this in the greenhouse, and we'll see how well it works. Thank you.